Okay, good afternoon all. We'll be starting week 4 tutorial for stochastic control and communication. I am Apurva Dhingra. I am a PhD student in IIT Bombay and I'll be taking this session. So, before we start, do you guys have any doubts from the previous tutorials or the lectures or assignments or anything so far? Okay, alright. I'll quickly take a recap of what we talked about in week three's tutorial. So, we started out by looking at the different types of policies: Markovian, history dependent Markovian policies, history dependent deterministic policies, randomized Markovian policies, randomized history dependent policies, and so on. And then we spent most of the time going through one example and enumerating at least one policy of all of these kinds. There are four different types of policies that we talked about, and then we wrote down what are the ways of getting those policies. How do you enumerate them? Then we talked about the number of, this was example 2, this was the same as lectures, so we didn't spend much time on this. um, we also talked about the number of policy search that is required to find the optimal strategy, and we saw that number was actually quite big. It was a to the power b times n, where a is the number of actions, b is the number of states, and n is the time horizon. So that's a huge number. So today we're going to talk about this principle of optimality, and that it gives us an algorithm that is called dynamic programming. So let's quickly revise what this principle of optimality said. This said, we can take an example and focus on the point. This particular principle of optimality basically says if you want to go from node A to node B, and let's say this yellow path, the one that is highlighted in yellow, is the optimal path, then for any intermediate node along this path, for example this one or this one, it's the same yellow path that will be the optimal path. It can be argued very easily just in words that, for example, let's take this intermediate node. If there was a different path which was better than this path to get to the final destination, then we'd end up choosing that path in our final optimal solution in the first place. This would just be not chosen, meaning this is the best possible path available, even if we're not talking about the full trajectory, we're talking about only partial trajectory. And this exact idea of having partial trajectories and using that to find out the optimal from this end point to a starting point gives us a method of using this structure of the problem itself. And by structure of the problem, I mean this additive structure, that the rewards are rewards or cost, whichever language we are using, it's added for each time step. So now let's go to this method which will be actually using principle of optimality, called dynamic programming, and that's the main thing today. So recall, the thing that we're trying to minimize in the language of stochastic control at least is this: the expectation over some randomness. So those randomness could be w1 till wn, where we have some terminal cost for the terminal state xn, and for every other state we have some cost incurred. It could, I could also start from 0, it's the same thing, it doesn't make a difference. So I ui and wi. Recall wi was the noise. This was the noise term. This is the action, and this is the state at time xi. So at time I. Now this is minimized over the function space, the functions of. So if I am focusing on ui, so ui is some function mu I, which is a function of xi, and this is for all such mu 1, mu 2 till all those mu n minus 1 coming from some policy. We would have chosen what kind of policy we are talking about. So that's what the minimization is over. Okay, this is the main objective. This is our main task. Now, what DP gives us is a method. Just hold on. So DP just gives us a method of calculating something which is called as the value function, which is denoted this way. It is jk of xk. Now it depends on which state you're talking about. So it has something for every state, for all the states that are available. So this turns out to be okay from now here inside there is a jk term, but of the previous one. So dynamic programming basically starts from the end point and it goes backward. So it's a kind of a backward induction. So we would actually start from the nth state or the terminal state, and we would say for the terminal state this value function is just jn of xn, is just some gn of that particular state. So if we are at some step k, we would be looking at the value function one step before meaning k plus 1th value, and that would be and we'd be getting some state here, and that state would be a function of these guys. This is what we are ultimately doing recursively. So this is the value function, this is step 1, and this is the subsequent steps. Okay, yes, what was the question?
Yeah, so I had a thought experiment, like what if instead of optimizing this function gn plus summation of all I goes from n minus 1, stage wise cost we optimize state wise. For example, at the ith point, whatever g was there should optimize, and whatever policy I consider as a inside this. Then I made try to apply this principle of optimality. I did math. I found that it has to be fully connected network, because there could be one state where I reach but I can't go back. So but my doubt here is this only true when the network all nodes are not fully connected. If it is fully connected, can I go with stage wise optimization instead of adding the.
Okay, first thing that I should clarify here, what you're describing doesn't sound like a dynamic programming approach, it sounds like a greedy approach. But this is what I understand you're saying. At every node you're choosing whichever is whichever action gives you um, the smallest cost, for example, you just go with that. So you're choosing locally, you're not looking what it would lead to 2 steps ahead. It is possible that in the first step that you're choosing, you end up with the choice where the cost is, let's say the cost is something negative. So you're like, okay, you've probably chosen something well, good. But 2 steps later, it is stuck in such a way that it leads you to the total sum being more than what you would have ended up with the other two options. It's very much possible.
Correct. The
So
thing is,
here, this approach actually doesn't work in a general setting. What you're describing is a greedy approach, and that's very different from what we're talking about here. This is looking at the whole problem backwards and using that idea that we can look at the problem backwards, which is what the principle of optimality says. This algorithm is designed. So your
because
algorithm is different itself. So yeah.
Mhm. I was trying to search like maybe a proof or something like this method and greedy method at the stage wise, whatever outcome comes and this outcome comes, this will be more optimal than that. There was no proof available as of now. Even in class, we use induction directly. We started with this and we apply induction over there.
Okay.
We did not start with the general version, right?
Okay, hold on. See, sometimes proof is not what you require. If you want to prove something that it is true for all cases, then you require a proof. But if I want to just disprove your point, I can show it with one example. Agreed? One counter
Yeah,
example is enough.
that
Yeah,
example you have given.
yeah.
Uh,
So it's not
but
enough.
yes,
Greedy
correct.
approach will not lead you to a global optimal minimization of some cost. So that's it. It'll
Yes,
not work.
exactly. I agreed that the example was good. The thought experiment was, what if these two are same? Then how would my structure would be? So it turns out I'm feeling like it is fully connected thing. Like every nodes I can reach to other nodes. When the greedy outcome and then this outcome both are same. Like it's a thought experiment only. I don't have full proof and structure wise. I'm working on that. But if both are equal, how system will be like? This is a thought experiment, and I don't have answer finite.
Um,
By
See,
the way,
so
is it making sense? The
a little
question,
bit.
like,
So you're saying, what if you end up with a problem which is such that your greedy approach and your dynamic approach gives you the same optimal value, right?
exactly. Even policies, everything same.
And then you're saying what kind of problems would create such a situation.
Yes. And can we utilize this? Can we do
In
this?
this, see, in the scenario that we're describing, DP is more general than greedy. Greedy is something that is applicable when you're talking about problem that can be made local, that locally choosing the best option is the best option overall. If that is the structure of your problem, greedy is the better choice because it'll be less compute expensive, it'll be easier to solve, you'll not have to store something. But in general, the kind of problems that stochastic control deals with, or the kind of problems that are dealt with in the MDP planning type work, uh, it, there's no local structure assumed. They're never saying that you can make the best decision at one step at a time and you don't have to look ahead. That's an easier problem. So for a general setting, it's DP that is typically more useful. Now this is more like a DSA question, in what kind of problems greedy works better than DP. There can be other answers, like you're saying, in connected graphs maybe it is possible, but yeah.
Okay.
Okay, so where were we? Okay, so the steps in this algorithm is, first step is we're going to we're just going to look at whatever is the terminal cost, and that gives us what we're calling as the value function of the terminal cost. That part is straightforward. Then we go one step ahead. So from n, so if there are total time horizon starts from 1 and goes up till n, we look at the step before. So we look at n minus 1, and then we find out what is j n minus 1 for whatever state there is. So whatever is the state space for all of those x's, we'll have to find out what is j of n minus 1. Once we do this, once we optimize this particular type of an object, we will get something optimal here. We'll get the optimal action here, which is just argument of this guy, argument of this object. Right, UK can vary as a function, that's fine. Whatever we got here, now this is something that we're going to keep using. In the next step, we'll go to, so first we got this, then we got whatever is happening. We're optimizing over 2 steps now, so n minus 1 and n. After that, we'll optimize over n minus 2 till the last point. So we are increasing what we are optimizing over. So if you go back to the example that I gave earlier, just a second. So if you recall the example that I gave earlier of going from one point to another, all we are doing here is we are saying if this is my xn, I take one step back and see where would I have been one time step before to have to finally end up in B. So I look at those states and then I calculate this value function for all of them. In fact, here we calculate for all of them in general, no matter, we're not focusing on just the previous one, but we're looking at what happens one time step before. Then we go one more time step before. So we might have been somewhere over here. And then we go one more time step back and so on. So we're optimizing, we're finding, okay, between these two, which is more optimal. So we say, okay, it's this one that is more optimal. Then having already figured out that this is the more optimal one between these two paths, we use that information over here. Like which one is better to choose, this one or this one? What does it give us, this path and this path? So we say, okay, this is the path that we should be choosing. To make it more precise, let's say there is a node like this also. So there are 2 options here. Then the choice is being made. Which one to choose? Whether is it, this one is already being chosen, whether to choose this one or this one. So in step by step, we're finding out what is the trail of policies. So we start from finding out what is un minus 1, then we find out what is un minus 2, till we are able to get till mu1. So this way we get the full policy. If we pause in between, then we would have a policy by k. This is just notation, nothing more than that. So that would be, again, we're starting from the back and doing backward induction. So we would be at mu k. Is this point clear? So this is just an intuitive idea of what we are up to, what this dynamic programming is all about. Now, the reason why, apart from the fact that this comes from a theorem, this came as a result of a theorem, one more reason why this is actually helpful is because if we now look at the number of computations required in DP and compare it with the search that would have been required if we were to search over all policies, you'd see a dramatic change. So if you recall, what were the number of policies that we had to search over? Let's say we were dealing with deterministic Markovian policies.
For n epoch, a to the power bn.
Yeah. For n epoch or n time step, it's a to the power bn. Now, what is the number of computations here? In in this particular part, in the DP algorithm, what is the number of computations? Okay, let's look at it this way. Let's look at a general scenario. Let's look at this one, JKXK. Now, first thing that we should notice is this needs to be evaluated for each xk. So that's point number one. Now, whatever this quantity is, we need to do it over all the possible actions, right? We're minimizing over action, so we need to know the value of this expected utility value for all actions for a given state. And we know that there are total whatever the number of states, so we're supposed to multiply those two, and this is just for this whole step is just for one time step, one value of k, and we need to repeat it for the number of horizons, whatever the number of horizons are, which means the total number of commutations that you'd have to do for a DP type calculation is a times b times n. Now look at the dramatic change. Here everything is simply multiplied to each other. Here they are exponential. So one of the benefits of using DP is by using the structure of the problem, which is the additive structure, this particular structure, the number of computations needed to get to the optimal is reduced significantly as compared to searching over all the policies, and that would have required us to do huge computations. Yeah.
Okay, I just a doubt, like why are we keeping n? Because the last stage we are not computing anything. It should not be n minus 1.
Sure,
Like
sure,
a
sure.
times.
That's just a technicality, nothing to worry about there.
Okay. Because the last stage we don't compute anything, right? It's just
It's
given.
okay. That's just a, in big orders it won't matter that much. Happy?
Correct. Because in the initial state sometimes it's given, so n minus 2 also possible.
That's not a significant enough change. The point is we're going from something exponential to something that is linear in a, b and n, all three of them.
Correct.
So the compute has reduced significantly. Okay, so okay, why did I add this page? Okay, so now I'll not go over the proof. The proof was done in the lectures and it was fairly straightforward in my opinion. I'll just go through the idea, the core idea that was pointed out in the proof, and that's all I'll focus on. Okay, so recall what are we supposed to do. The steps are: step number 1, we find out what happens at Jn. We find out the value function at the last time step at the terminal state. And by the way, there is no restriction. This can be for any terminal state. In fact, it is for all terminal states. Okay. Now, why does this thing work? Why? So this is basically saying at the end of this process, once we have reached j1 of x, whatever, x1 for all the possible states, what we would have is the optimal solution. Now note, I took I equal to 0, I starting from 1. That's why I'm saying j1 x1 would be the optimal solution. In the lectures, I think I was starting from 0. It's just a technicality, nothing more than that. So point is, at the end of this DP algorithm, we get an optimal value, and at each step we are getting the exact policy that is the optimal policy in the problem. Okay, so now let's go over the, not the details of the proof, but just the core idea. Okay, so the proof basically focused on looking at things by induction. What they're saying is, let's say first step is fine, we're just taking the value to be the terminal cost itself. That is fine, we're just choosing at the terminal cost. There's nothing to be chosen, just one step before how do we get to the terminal cost or the terminal state, that is, there is some choice there. That's about it. Now what happens here is, let's say we are focusing on some policy pi k. Pi k meaning it has all the steps up till n minus 1 and it's starting at k. So as per our example, between a and b, we are at some in between time step and we are choosing which path to go for. Okay, so at some time step k, optimal policy has been chosen, which is what is denoted by this symbol. In the video, sir shows that the optimal, which is optimizing this guy, optimizing this particular quantity, the expectation over terminal cost and the sum over all the other cost, minimized over the space of policies. This is the same as doing this backward induction process. And this backward induction process mainly looks at the cost at that particular time step and the value function at the time step k plus 1. So when I say the time step k plus 1, what I mean is it looks at time step k plus 1 onwards till n or n minus 1, and that allows us to find j of k. Okay, so the way to go through the proof is very simple. He starts out by saying, okay, that we have some optimal jk plus 1. Using that, he plugs in that value in this equation and simplifies. And he ends up saying that it ends up being exactly equal to, after simplification, it ends up being exactly equal to this. That's it. So remember, what was shown in the proof was at each time step, whatever jk of xk we get, which is based on this equation, whatever it is that we get is actually the optimal from starting from a particular node, some intermediate step in the process, till the last step or last terminal steps. So it has the idea of principle of optimality in the background, which is why this is the same as the optimal value of jk for that particular state. Is this okay?
Yeah.
Alright. So now let's look at one example. If you recall, we saw the example of inventory control some 2-3 weeks back. So now we're going to apply this DP problem onto that problem. So first I'll spend some time describing the details of the problem, what exactly it is and so on, just like it was done in the video lectures also. Then I'll take a couple of examples, not a couple of examples, I'll basically take one example and solve the whole example. This should clear out if you have any doubts from what was done in class. Also, if you have any doubts for the upcoming assignment that you have. Okay, if time permits, I'll talk about this whole thing from the perspective of MDPs also. If not, then that can be taken up next time. Okay, so in the inventory control problem, what we had was, we had some stocks available at some time interval or before some time interval k, then some stocks were ordered. Ordering or purchasing was the action. We were assuming that the delivery was immediate, which allowed us to not have to worry about time it took to get the delivery, how much delivery we got at any given time, was it the current delivery or the delivery from the previous order, all of that we didn't worry about. And then WK, which is the demand at time K. Here, the assumption still holds. All of these W's are taken to be independent of each other. The sequence is first XK is available, then UK is ordered. XK is available, matlab the value is realized, that it's known what are the number of stocks in the store at any given point of time. Then the needed stocks are ordered. Then in the next time step, or maybe like the next day, or at a certain after a certain interval, demand arises, which means the value of the demand is realized. So this is the randomness in our problem, and this loop keeps on going. For the loop to go on, the dynamics of the problem is taken to be okay, I've not written the dynamics of the problem. So for this particular situation, let's say backlogging is allowed, which means the next value would be the stock available right now, what is ordered, and how much of it got consumed in the demand. If backlogging was not allowed, we'd just take a max between this value and 0. Okay, backlogging allowed means that this can actually take negative values. If that was not the case, we'd just put a max and that's about it. Okay. Now, the problem is designed in such a way that there are 3 components to the cost. First cost is some sort of a storage cost, depending on if there is like extra stock available and it needs storage, or if the stock that is needed is less than what is available, there's like a negative stock, there's some sort of backlogging, then there is a penalty for that. Both of that is encountered or taken care of in this R function. This R function can either just depend on xk, or it can depend on xk, uk, wk, all of these things. In general, it can depend on all of them. Here we've taken it to not be dependent on all of that. Both of those are equally okay. Next is, if some order is placed, then what is the per unit cost of the item? Now, typically this cost is taken to be a constant value and it's multiplied by UK, but there is also a possibility that the cost could itself become a function of UK. That if the number of order placed is more than a certain amount, then you get a wholesale price, otherwise you have to pay a higher price, and so on. Then there is a terminal cost, R of xn, and our goal is to minimize the expected cost after n time steps, which is this. Okay, now what we're going to do is we're going to apply DP to this problem. So what DP requires us to do is we have to start from the end. So we look at the terminal states. So it gives us what should be Jn of xn for all those terminal states, and that is just the cost. So we have defined a terminal cost, and that's all it is. For any other time step k, the general thing that we're supposed to do is we're supposed to minimize over the action, and what we're supposed to minimize is okay, let me write down based on this example. So this is my gk of xk, uk, wk. So this is r of xk plus C times UK. Okay, and then there is the quantity, which is whatever happened one step before, or in the K plus 1 time step, and the dynamics of that time step. And we already know the dynamics, so the dynamics is xk plus uk minus wk. Now, depending on the way the problem is defined, we have to focus on the part that has some randomness and the part that is getting optimized. Anything that is not getting optimized, we can just take it out from our description. Take it out of the objective function and can still keep it for the sake of comparison. So here, if we were to write out the steps, right, if we were to write out the steps, we started with n, now we'd go to n minus 1. So at n minus 1, we have to minimize u n minus 1 for the set of values that it can take. But recall, this actually is just, we have never said anything about what kind of values it can take. The only condition is that u n minus 1 or any of these u's should be more than 0. The demand that is placed is positive. So this u n minus 1 is just more than 0. That's about it. Now here I'm supposed to put the value as k plus 1, which is n here. So it's jn of x n minus 1 u n minus 1. Now here, the thing to notice carefully is this particular term, the first term that we have in our expectation. This is something that has no randomness in it. This is just a value that is not realized, but this is just a parameter, and we are calculating the value function j of whatever at whatever time step for all of these. So that is all it is. So this component is something that is not random, so we can actually take it out of the expectation. And un is the action, so there again there is no randomness as such. The only source of randomness is over here. So we could simplify this and write and another thing to note over here is this x is something that we have taken it to depend only on the states, and we have not taken it to have any dependence on the action that were taken. So technically this is not getting minimized at all. So we could rewrite this as there's a plus sign here. Of course, if the way our problem was defined, the R had some dependence on U and W and so on, then we'd have to keep it inside. We'd have to keep it inside the expectation, and we'd also have to keep it inside the optimization that is being done. But here that's not the case, so we could just take it outside. Now, the exact same step could be repeated, and we could get Jn minus 2. Oh, by the way, note this is for all xn minus 1 in the space of states, from the space of states. And this process continues.
In this scenario, we are not, or maybe I am have this doubt, like we are assuming minimum value exists because R of n is not minimizing parameter, okay, but J of n could be any other very notorious value which minima does not exist. Let's say linear function. Minima could be infinity, minus infinity.
That is
So
possible.
minima does not. So how this structure, or is it just a general example?
This is a general example. So what happens in a case where minima doesn't exist, or we're not able to find a bounded minima? Then instead of minima, we could be focusing on infimums.
Okay. Okay. And this every time writing mu and minus 1 greater than 0, like we can treat this as a constraint and add as a Laplace, this Lagrangian multiplier.
You could do that.
Like that will be easy for
solving purposes, yeah.
Mm-hmm.
That might make it into an optimization problem that you can solve in a much easier way.
And there are Python solvers, MATLAB solver. I can plug there and then get the values.
Yeah.
Or we have something else.
For now, this is what we're talking about. We're not talking about any better tricks, at least not this week.
Okay.
There are other methods, but let's see which all methods come up in the upcoming weeks.
Okay, thank you.
Yeah, so I'll continue. If you people understood this much, I don't need to repeat it for the next steps. It's the exact same thing, just for every trait. That's about it. So we can now take an actual example and go through the details of that. Alright. Okay. So now the example that I'm considering is as follows. So in my example, I am allowing backlog. Backlog being allowed means this is the dynamics. And I'm putting a few constraints so that I can actually make things solvable and then verify whether it is actually possible to solve or not. So I'm saying that these values, first of all of these values are supposed to be integers. And for WK, I'm saying that this is either 0 or 1. That is it. The demand is either there is somebody or there is nobody. For the action, I'm putting a constraint which says the sum of action and the stock is 2. That the stock cannot be more than that. And the conditions that I'm describing here are almost the same that were taken in class, except this one. What was taken in tutorial was backlog is not allowed. There's a reason why they took that example, and I'll come to that point. Let's assume that backlog is allowed and see what happens. So for my problem, I'm assuming that the distribution over WK is as follows. My initial state is x0. This is my initial state. The storage cost or holding cost is something that depends on xk, uk, wk, matlab, as in all the things that describe what will be the value in the next iterate, the stock value at the next time step, whatever that is, the prediction of that is used to find this function, which is just taken to be a square of this. And the additional cost is such that per cost of the stock value is just 1 units, and terminal cost is taken to be 0. To make sure that this problem is something that we can solve in our time here, so I'm taking n to be 3. Good so far? So now our main task is to understand what is the state space, because state space is, even though restricted, that space, this can be some integer values. We need to see what integer values are allowed by the description of the problem, and based on whatever tools we have, can we actually solve for it? Can we use dp and solve for things? Okay, so this is our problem. This is our problem. Now if the restriction, if x can take negative values, but u is supposed to be such that uk plus xk is, it's supposed to be less than or equal to 2, what can you say about the state space? What all values of xk are allowed?
Mainly 0 to 1.
Mm-mm. Why 0 to 1?
Because if it is more than 2, UK will be negative numbers.
Okay, let's make that argument more carefully. So what I'm saying is uk plus xk has to be less than 2. What about the situation where I take xk to be something negative? So let's say something like -5, and I am saying uk is 0. Is this within the constraint?
Yes, yes, yes.
That means xk is allowed. Now let's say I add wk to this. My wk is just 0 or 1. After adding, is it still allowed?
Obviously, xk plus 1. Yeah.
Meaning my xk plus 1 now became -5. Let's say uk is still just 0 only. It became -6. And there's nothing stopping it from going in negative values. Which means it can
Okay,
go till all
then
the...
xk range will be -infinity to +2.
Exactly. So this side, it's going to go all the way till -infinity. On this side, like you said, when xk is equal to 2, let's say what happens. Let's make sure what happens. So let's say xk is 2, uk is again 0, and wk is 0 or 1. Then it either stays at 2 or it becomes 1. Xk plus 1 takes these two values, depending on which wk was encountered. Meaning if it reached 2, it's not going to do much. It'll either stay there or go to a smaller value, but it'll never go to a higher value. So the range of xk is that it is less than 2. Now this is not a finite state space. Whatever we have been talking about, we can in principle solve it. In principle. But actually doing this computation is not possible because my state space is already infinite. So either we need to come up with a way to argue that beyond a certain negative value of xk, uk will be some specific kind of action. That's the only one that will make sense. But this cost will keep increasing. Right? We have this terminal cost in our jk of xk. If xk is more and more negative, this, whether 0 or 1 doesn't matter, let's say this is the best possible, which is 2, even then this value would keep on increasing. So beyond a certain point, clearly um, will not be able to make any strong arguments about optimality lying where xk is negative values. But nevertheless, this is an infinite space problem, so this is not so straightforward to solve. For this reason, I'm going back to the example that sir had. Okay, so I'm going with that variation where not allowing backlog. The other details are as follows. So what I have changed is this part.
Is this argument valid for omega k also? If omega k also have an infinite possibilities, like 0 to infinity omega k.
If
And
omega k had that much, you'd basically not be able to compute this. Actually, yeah. If omega k was allowed to be infinite in this exact example, then your xk would be affected accordingly, or xk plus 1 would be affected accordingly.
okay.
So,
Because I can apply some continuous mass function on omega k and which will be infinite in value.
you can. So, that's the reason why, at least for the sake of arguments here, we're taking everything to be simple that we can actually solve. So, like I was saying here, in this example itself, even with infinite space, it is possible to solve. But the arguments, proving those arguments is a tedious task, and it'll only be dependent on the exact form of the cost function that we have taken. But to skip that part, because the whole point right now is to show you how this is to be calculated in different scenarios, so we'll not get into all of that. In principle, it's possible. Okay, so like I said, the variation that I am going to focus on is where backlogging is not allowed, which means the dynamics of the problem is slightly changed. Now the dynamics is xk plus 1 would either be 0 or this one, xk plus uk minus wk. This would only be taken when this value is positive. Just 1 second. क्लास में हूँ. Okay, where were we? Right, so in this particular variation, we already know, so our number of time steps are 3, so we are starting with k equal to 3, so j of 3 for x of n is what we are assuming to be 0 for all xn, for all the terminal states. Okay, now our task is to make the calculations for the remaining situations. So what are we supposed to do? Let's recall. We are supposed to minimize over u2, and u2 has to be greater than equal to 0 in general, but here we have a constraint, right? u2 plus x2 has to be less than equal to 2, so u2 has to be less than equal to 2 minus x2, so this constraint still holds. And we know x will take values between 0, 1 and 2, means u2 can take values 0, 1 and 2. Okay. Now we're supposed to take the expectation over W. This is W2. So there is UK, that was 1 times UK, plus, if taken x2 to be 0, so we just have UK minus WK square, and we have J3 of xn. Now this J3 of xn, for any value of xn, it's 0, so this completely goes away, so we don't have to worry about this term at all. All we are left with is this part. Here instead of k I should have written 2. Let me rewrite that. So this is u2, this is u2 minus w2. So this is just simply the value of u2. This doesn't have any dependence on w, so this can actually be taken outside. This is all that there is a dependence. The probability of w's two values are 1 by 4 and 3 by 4. So 1 by 4 for just u2 square and 3 by 4 for u2 minus 1 whole square. Okay, now our job is to look at the different values of u2, compute this, and see which one gives us the minimum value. We could do it in whatever way we want. So for now I'll just do the computation this way. So if u2 was 0, this would be 0, this would be 0, this is all, sorry, this would be 0, this would be 0, this is all that will be left here, and that would be 3 by 4. If u2 was 1, then we'd have 1 plus 1 by 4, and this term would be 1 minus 1, which is 0. So this is just 1 plus 1 by 4, which is 5 by 4. This is definitely greater than the first one. So we already know between these two, this is the better choice. But nevertheless, let's continue. Then the next is u2 being equal to 2. When this is the situation, it is 2 plus something something something. Both of those are positive values, so whatever happens, this is greater than 2. So we can already see the optimal here is this one. So what we got is J2 of 0 is 3 by 4. This is the optimal, and this happens with u2 equal to 0. And we're supposed to keep repeating this process for, first of all, we're focused on time step k equal to 2. So this is the time step k equal to 2, this one. We're supposed to do it for all the 3 values of xk. So we have done it for 0, we have to do it for 1 and 2 now. It's the same process repeated over and over again. If you do it for some time, you will be able to see the pattern also, and you can actually generalize it for n, but we'll stop at 3. So same thing. Now this time u2 is supposed to be less than or equal to, it's greater than or equal to 0 for general cases. This time it's supposed to be less than or equal to 2 minus x2, which is 1. So the allowed values of u2 are 0 and 1. Okay, what are we minimizing? It's 1 plus u2 minus w2 whole square plus j3 of xn. typically it's only in this situation that this term is 0, that's why it's cancelling out, it's just going away. Typically this might stay and have dependence on w's, and we'll see that coming in the next time steps actually, but for now this is again 0. Right, so now this is what we're supposed to minimize. So this is u2 plus 1 plus u2 square with probability 1/4 when w2 becomes 0, and with probability 3/4 this is just u2 square, and we're supposed to minimize over this. So when you do that, what will you get?
At 0 it is minimum.
Again, correct. At 0 it is minimum, and what is the minimum value? j2 1 is
1/4.
j2 1 is okay, good. Okay, same thing we have to repeat for x equal to 2 also, but x equal to 2 is even easier. Now here, what are the allowed values of u2? u2 can only be 0, that's it, there's nothing else that is allowed. So that's it, we just have to compute this for u2 equal to 0. So that is
7/4. But anyway, when I calculated for 1 and 2 also, it is very high. Like I did calculation for u2 is equal to 1 and 2 for j3, x is equal to 2. It is out of range only, but there is no point. Those numbers are very high.
What numbers?
J2, x2 is equal to 2 for u2 is equal to 2 case.
But u2 equal to 2 is not valid.
Not valid, yes, I agree.
I mean, we've put a constraint. Otherwise, yeah, sure. This be 1 plus u whole square. So you could plug in the value and see what it comes out to be. Did I make a mistake? What value are you getting?
7/4.
7/4.
The equation is correct. If you put u to 0, 1/4 will be 1 plus 3/4. That is u2.
Okay. Yeah, that's u2. Right, so you get 7/4. Okay. So, right. This is just 1, this is 3/4, right. So these are the three j values we got. These are the optimal j values, and we got all of them for u2 equal to 0. So that's the general point here. Now we're supposed to repeat the same process, but for the next time step, meaning for k equal to 1. So it focuses what happened from 1 till the end. So the end for us is k equal to 3. Now here we have to be a bit careful.
In second tutorial or somewhere you mentioned that in chessboard every possibility you consider as a state. In that scenario we need to calculate everything.
Which example was that?
In the chessboard every possibility is considered a single state.
Yeah, every possibility. Okay, so for the chessboard, every what are the names of those objects on the chessboard? Every positioning, every configuration of the chessboard is one state. and there are a huge number of them. It's not infinite, but still the state space is fairly big. In principle, yes, but people don't actually sit and do those computations for an example like chess. When the state space is too big, going by this method is actually not the best way. There are other smarter methods.
Okay.
So the point is, this method will give us the optimal value and the optimal policy that leads to that optimal value. With smarter methods, we would be saving compute or saving resources required to do calculations, but we may not get the exact optimal values of the, as in the optimal value and the optimal policy. We might be getting something approximate, which is not too far from the believed optimal, which is, in that sense, it's okay and acceptable. And that's how people generally work in these scenarios, like reinforcement learning or MDP type scenarios.
Okay, interesting.
Yeah. Okay, so let's continue. Now what we are doing is, for the time step k equal to 1, it's the same process that we have to repeat. Let's say x1 is 0, so u1 will be 0, 1 and 2. But this time, the j that comes up here is going to be j2, which means it's going to be these three that will show up in the calculations further on. So it's going to be j2 of, now it's the off part also that is important. We didn't have to worry about in the previous case because all of them were just 0. Here it is max between 0 and x is taken to be 0, so this is w1 minus this. And one way to handle this is to calculate this taking exact values of u1. So we could do it this way. So let's say u1 is 0. If that is the case, then this is 0 plus 1/4. Both of them are 0, so there's nothing here. Okay, 0 plus, which means we have to take j2 of the 0th state. u1 and w1 are both 0, so this is just j2 of u1 state, meaning it's going to be 3/4 that we're going to use here. And with probability 3/4, it's the other situation where w1 is 1. That gives us 1 square plus j2 of 1. And then we have to plug in those values and solve for it. Okay, so what would this turn out to be? Oh. That looks like 1/4, 3/4, 3/4, 1/4. So that's 9/16. Oh no, not 9/16, 6/16.
Yeah, 6/16.
Yeah. Next, we're supposed to repeat this, but we have to take u1 equal to 1. When that happens, the j value would be 1 plus, with 1/4 we get with 3/4 we get 1 minus 1 is 0, so j2 of 0. So this is 1 plus 1 by 16, and this one is 9 by 16. Nevertheless, u1 equal to 0 is the better one amongst the two. Similarly, we need to repeat. Oh, okay, my calculations were different before, never mind. So for u1 equal to 2, we're supposed to repeat the same process. We would get 2 here with 1/4 probability. It's u1 minus w1, which is just 2 square, so 4 plus j2 of 2, and with 3/4 probability we'll get with 3/4 probability we'll get 2 minus 1 1 plus j2 of 1. If you do this, this will be bigger than 2, so we're still fine. The optimal is j1 of 0, optimal is 6 by 16 for u1 star equal to 0. Now you're supposed to just repeat the same process for j1 1, j1 of 1, j1 of 0, and j1 of 2 for all of them. You'll get some values. I think my values, the ones that I've written here, are not correct. But anyways, you'll get some values and you'll find out what is the optimal policy for each of them. The only thing here is, because we had a condition on what is the optimal, what is the initial state we started out with, for j0 that's all we need to calculate. We don't need to calculate j0 for all the states. And once you've done that, you'll get the optimal throughout. So do you want me to do the rest of the calculation, or is this fine? You can continue doing the remaining on your own.
Whatever we can do.
You can do? Okay. So remember, here our assumption was the U's that were there, the actions, or the purchase orders that were being placed, they were integer values, or to be more specific, they were whole number values, so 0, 1 and so on. That's not necessarily the case. Even fractional values might be allowed. So if fractionals are allowed, you just have to tweak it and plug in the values and see what happens and optimize. So whatever the constraints of the problem might tell us what how are we supposed to optimize it, but otherwise this is still doable. But at each step you're supposed to optimize and get jk of xk, and you're supposed to do that for each xk. So by hand, obviously this is a lot if the state space grows a little bit, but computationally this is doable. Alright, now let me talk about one more thing. So this wasn't covered in the lectures, but I'll just talk about what happens if you have an MDP. Like, remember, whatever we are saying, we're saying that MDP, a Markov decision process, can be converted into a stochastic control problem and vice versa. We know how to do the conversion depending on what our problem is, how it has been defined. If that is the scenario, since we have a learning, we have an algorithm right now which is a dynamic programming algorithm. So what kind of an algorithm will show up in case of MDP type problem? So that's what I'm going to talk about now. Alright, so if we are talking about an MDP, this is the part that I've already written. Okay, let's see if we get to the problem. So if we are talking about an MDP, we have a state space, we have some actions available, actions corresponding to each state in the state space. So A here refers to union over small s that belong to capital S, and AS for each of those states. Then we have some transition functions. What is the probability of going to some state if originally we were in state S and took action A? So this type of information is available for all the states. That's the part of the description. And on top of that, we have some reward function. That reward function tells us if we are in state S, we take action A and go to some new state, what is the reward in this scenario. We also know that this reward can also be converted into the expected reward, which is just based on the current state and the action taken at that state. Both of those are same things. Now, just like we had a value function in stochastic control, we have a value function here also. This value function is denoted as follows. Okay, let me rewrite this. This has gotten quite messy. So what this value function is focusing on is a particular policy pi. This refers to policy. And in MDPs, at least all the things that I'm going to talk about right now, I'll be focusing on Markov deterministic policies. So this pi is a Markov deterministic policy. It starts from some state space and gives us the next action to be taken based on just that one state, nothing more, no history, not a randomized policy either. It just gives us one deterministic next action to be taken for that given state. Okay, so this guy is expectation. Now here very clearly we have a distribution on the next state. So the expectation is with respect to this probability only, the transition probability. In this expectation, what we are interested in is this reward at state, let's say we are focusing on state SK, AK, and we are going to the next state S dash, or let me rather call it SK plus 1. And K starts from, let's say it starts from 0 till n minus 1. And there may be a extra reward for the terminal state, for all terminal states. This expectation, when calculated, assuming that our problem started, the initial state in our problem S0, if we assume S0 was the state S, then what we get is called the value function in the MDP language. So here very, very precisely saying what we are referring to as S. S is the initial state.
But that means the value function is a random variable.
It's not a random variable, it's more like a function. It
Because
depends on where you're starting from.
conditional expectation is a random variable in itself. So, but S is fixed. Yeah, it should be a random variable.
Okay, I understand in what sense you're saying. Sure, it is. But so we can think of it like a simple function which depends on where we're starting the problem from. Obviously, if we start the problem from a different place, we'll get the value function to be different. But we're saying that we're focusing, we're calling it a function, which is fine.
A random variable is also a function,
The
but with a
starting
different
random variable
characters.
is not, so there's no probability defined on just s. The probability is defined on s given an action.
Correct.
In that sense, nothing more than that. Okay, so my claim is, this is something I'll prove in the next I'll prove below, that this thing, this value function, has the exact same form as this. And to find the optimal value function, what we're required to do is just take the max over u. Don't worry, I'll go through this step more carefully. This one is a statement I'm saying. I'm not going to prove this. Yeah, I'm not going to talk more about how we got this or what exactly is behind this. There's quite a bit of theory there. Okay? Alright, so if you were to write down this value function p of pi, let's do this. I'll get rid of all this and start again. Okay, so we can write our value function in this form also, right? Here I've written this as a summation, and I've included the terminal cost, or the terminal reward to be more specific in the MDP language. Here I'm saying let's just take a sum over all of them. That's the same things. And Rn here means whatever is the terminal cost. And this is starting with initial state S0 equal to S. Alright, so now I'm saying I can write the same value function in the following way. Instead of just taking the condition on the initial state, I'm also conditioning on the next state. So I'm saying what is S1? What is the next state? I'm saying it's some S dash. Whatever state is allowed, whatever state I'm allowed to go starting from S0, all of those S dashes, that's what I'm summing over. Fine. This is a valid step. I'm taking this expectation, bringing one more conditional, and because I've brought in one more conditional, I'm just summing over the probability of those.
Then this S dash should be from same set, right? Like same sample space. Otherwise you can't do.
Let's assume it is.
So which means S could be, okay, it depends. Yeah. Perfect.
They're from the same. Yeah. That's why I'm saying there's a lot of assumptions here, and I'm simplifying a lot of those things. Okay, so now let's rewrite this. So this is the same as here notice action is replaced by what the policy gives me. Because it's a deterministic action, I've just plugged it in here directly. Let me just split this. me write it like this. This is S1. I'm saying this is the same as some S dash. Okay. This is just first pass. This is using the linearity of expectation, nothing more than that. Then the other term would be now notice the first term. What is that?
First term of what?
This first term. What is this?
This is expected reward.
Everything is expected reward only, yes, but this is telling me something. This is very simple.
So on an average reward, when you transition from S to S dash with a policy pi.
If you know the policy, you know the initial state S0, and you know the next state, you basically know all the three things required to define the reward, right? So there's no more randomness in that reward. So this quantity is no longer random. This is just the value itself. Understood?
Okay, wait. This is now becoming complex. Okay.
Yeah.
This is, we are making only Markov case, right? Okay.
Yeah. Like I said that earlier also, we're restricting ourselves to Markov deterministic policy.
Okay. Then makes sense. Because everything known, all three.
Now that everything is known and reward is something that is not depending on time steps.
But this
After knowing all that,
R0, this R0, the domain is S0, S1 and pi only. Oh, yeah, correct.
pi is fixed, right?
Yes.
It's for a fixed policy. And we know the initial state already, so we technically know the action also. It's a deterministic action. Fair?
Yeah. Fair.
Okay, so that means I can rewrite the first term as follows. First term is nothing but reward S, pi of S and S dash. Now notice the second term. It's starting from reward R1. R1 basically means reward for state S1. Action taken with that state. So now we don't know what is the action taken at this state. Or maybe the policy does give us that. It decides for everything. And the next state. The problem here is we don't know what is the next state. But for us, the initial state is now S1. This is R1. Meaning, there's no use of knowing what was the initial S0 that our problem started out with. For us, the real initial of this problem is just S1 now. Making sense?
Correct.
Which means I can rewrite this term as nothing fancy in this step, just removing this. Now look at the definition of v pi of s and look at this.
Recursive pattern emerging.
Exactly, a recursive pattern is emerging. That means v pi of s is actually something we can simplify and write as, this is common, right? So I can just copy it. The first reward and this part, v pi of, now instead of s, this is s dash. If we have this, then it is possible for us to say we are interested in a policy that maximizes this value, which means while maximizing here we would take v star, the maximized one. Okay, just one second. This is the part that I'm not justifying, but I will just make it as a claim and stop. So v star, or the optimal value function for any s, is you maximize. Remember, we are talking about reward here, that's why there's a maximize, nothing more than that. You're maximizing over actions, depending on whichever state we're talking about. So action coming from a of s. Now instead of policy pi, we're focusing on the particular action here. So whatever that a is, and we say we do this in such a way that we use the optimal value at some s dash. And this is one of the possible methods of finding the optimal reward in case of an MDP. Since this is more like improving the value itself, this method leads to something called value iteration. It leads to an algorithm called value iteration. But I think in stochastic control we may not go over the details of this. Okay, so the point that I was trying to make, the reason why I went through all of this before I go on to an example, is that just like in control, we saw that we can find this jk of xk, which was minimized over whatever we did today, remember? This is gk, some cost function at time k, which depends on xk, uk and wk. And what we add is the previous iterate, or whatever happened at the previous time step. And we use the dynamics of the problem to write down how to get to the next state. You can see, at least in comparison, these two are very similar to each other. Here the expectation is written out written in the form of expectation. Here it's just written out explicitly. That's one difference. Another, this is written in terms of time steps. Here I've written it directly. This can same in the same way this can be written as time steps also. So whatever is something that can be done in stochastic control has a parallel, has a similar approach that is possible in MDPs also. So okay, now I'll go over an example. This example is of an MDP. Again, a very small example. This may not help you with any assignment questions. This is sort of extra, but this will give you some more intuition about what exactly is going on. Okay, before I go any further, any questions in whatever I've talked about so far, especially in regards to MDP?
Okay, in this value iteration, R of n is necessary. Like R of n minus 1 should be there, no?
I've only forgotten that, nothing else. Oh, you mean this one? This R of n?
R of n minus 1 till that.
The terminal cost is taken care of in this part, in the recursive part.
Okay.
That's
Because
all.
it's independent of this probability now. Like action, at least action is independent.
Okay. So the pure terminal cost might just be an additive factor.
Yes, exactly.
That
Kind
additive
of.
factor can be there. I have just not written it. That's about it. Nothing else.
Okay.
So yeah, I've not written it. I wrote it here, but beyond that, I did not write it. You can just keep it as a additive term. Nothing more than that.
Okay. I'll try this proof by my hand, and next, can I ask question if I get down?
Sure.
Oh, thank you.
Yeah. Before I started this, I did say, right, this is extra. This was not something I saw in the lectures, but since he started by talking about stochastic control and MDP, gave both the formulations, showed examples in both, so it's fair to have some comparison of the two, because MDPs are the ones that you'll see if you're interested in the direction of reinforcement learning and so on. So I'm just giving you some of that. I obviously can't cover all of that in just tutorials, but you can go through the details on your own time.
Yeah, sure. Thank you.
Yeah. Alright, so let's take an example. Now, this, I think I had a similar example in some previous lectures also. It's the same one. Maybe I've made some minor changes. We don't have enough time. Let's see if we can finish it in 20 minutes. If not, I'll leave it for you as an exercise to complete the complete calculation. Otherwise, I'll at least go through the core steps, okay? So here, ST is the terminal state. These are the normal states, S1 and S2. The two actions are the following: the red action or this dotted action. And it's already written what is the transition probability and the reward. And the reward is written as going from initial state with some action to the next state. So in this form, the reward is written. And on top of that, let's just assume that the reward for the terminal state is just 0. So we don't have to worry about that. Okay, and let's try solving it for 3 time steps. Actually, I am not going to do it in an iterative manner anyways, so time steps are not that important. But if you wanted to, you could use DP approach with minor variations here also and try out what happens. So what I have been saying is, in this type of a scenario, we are interested in the value function. So value function, or the optimal value function for any state S, is given as follows. This is the maximum over the actions for the considered state. And we look at this guy. This is the S dash is the next available state. R of S A S dash. B star of S dash. Okay. If you're not doing an iterative version, you could try out an iterative version also. So let's do it for, let's start with the easiest case, which is terminal state. So for terminal state, it is V star of ST. There are no actions, so that part is not there at all. There's just this component. The terminal cost is taken to be 0, so the value also becomes 0. There's nothing else here. That was about it. Okay, but for the remaining states, this will be useful. So for V star of, let's start with S2. Okay, let me give some names. Action A1 and action A2. A1 is the dotted action and A2 is the action in red. So V star for S2 has both the actions possible. Now, to be able to compute this, we know this is S2, but that's about it. We don't know anything else. So we need to choose an action, just like we were doing in case of the control version. So we have to choose an action, find out what this is, and then, if possible, at this stage only tell which one is more than the other. So let's say A is A1. Then this value will be, there are two options. It either goes from S2 to ST or it stays here itself. It goes to the other one with probability 1/4. The reward there is 2, and we know the value function of the terminal state. We've actually taken it to be 0. The other situation is it has a self loop, and the reward for that self loop is 1. So it's 1 plus V star of, now the next state it goes to is itself. So it stays at S2. This is for one action. If it had taken the other action, the equation would be very different. Okay, if it took the other action. One scenario is with half probability it goes to ST. So let's write down that part first. With half probability and reward 2, it goes to ST. With the other half probability from, so for us the initial point is S2, that's where we're starting from. So from S2, where does it go? It's going to S1 and the reward is -3. That is written in the following way. Fine. Now if you notice, there are two things happening here. Let's be more careful here. If the action chosen was A1, we're getting this type of a scenario. This is 0.8 and 0.6, so 1.4, and this is just 0. This term is just 0, so there's nothing else. This term is the one that we're trying to compute. So what we are ending up with is .4 of this is this, meaning if this action was chosen, the value function of S2 would be 1.4 divided by 0.4. On the other hand, if it was this one that was chosen, this part, just the initial part 0.5 and 2 just gives us 1. This gives us a -1.5, so overall it's a -0.5. This term is 0, but this term is the value function for S1, so we can't actually make our choice at this stage. This is happening because of the max in front. On its own, this is completely linear in the sense this is linear in V's, this is linear in R, this is linear in the transition probabilities, but because of this max there is correlations, and that's the part that makes it slightly more difficult to calculate in certain situations, and we basically got to see that situation. Now we can't say which action gives us a higher value because we can't even compute this value independent of knowing what happens at S1. So we need to find out what happens at S1, use that here if that doesn't have any correlations with this one. So let's see what happens for S1. Okay, I'll just copy the diagram again. Okay, now we need to, okay, so conclusion here is we couldn't resolve which action should have been taken from S2. Okay, we'll try and come back to this later. Even though we have a value here, if this particular value can't beat this, this action should be taken. If not, then this action will be taken, and we need to know exactly what should be the value of VS1. Alright, so now let's try for VS1. We are supposed to repeat the same thing. So we're taking a max over the actions. Actions are A1 and A2. And we're doing the following. We're taking the probability of going to some state S dash, starting from S1 and action A. We take the reward from S1A till the state S dash, and we add the value function for the next state. Right. Okay, and now we're supposed to just repeat the process. You must have already noticed, even before starting the repetition, we'll end up in the same problem as before. Now, value function of S1 will depend on value function of S2, and we know value function of S2 already has a dependence on value function of S1. So this became a circular loop, and we're supposed to try and break that loop. But anyways, let's just write it down. Okay, let's take one action at a time. So let's take the easier action, which is A1. A1 has just one possibility, so this is easier. In this case, the value function would lead to, with probability 1, it's giving us a reward of 2 and going to state S2. This is it. So this is 2 plus on the other hand, if A2 is to be chosen, A2 has, with half a probability, it goes to 1. With half a probability, it takes this arrow and goes to state S2. With other half a probability, it stays where it is, but the reward is 0. So let's see what the loop now becomes. This is here it's a minus half, here there's nothing. So with half a probability, it goes to Vs of S2. I am taking this on the other side and leaving with a half here, which tells me now my comparison is between these two situations, and now this is doable.
But that also for action 2, B2 is dependent on VS1, right?
Right, but Vs, whatever happens, these two now have a very similar form to each other. Now the comparison is fair. We have a common term. It's the other term that becomes the deciding factor, which means this is the action that should be taken.
Okay, here it's possible. That side.
Huh. Let's first do this and then try and go back. So here we know what's the right action. Okay. So the correct one is now our job is to use this in those two and see if we can simplify them.
So it means, so the meaning will be like whenever in the S1 state, I should choose A1 action. Okay, that's the meaning.
Yeah, that's the meaning. Which is actually not surprising. Just look what is happening here. In S1 state, this has a positive reward.
Correct. Correct.
This
And I
and
is
this
probably
this has no reward, so this is completely meaningless. This has a negative reward. Why would you choose that? You're trying to maximize something, so you would want to choose something that gives you a positive reward. So this seems like a fair option.
okay.
Hmm? But anyway, let's finish the whole thing and then talk about it. So this we know for sure. This we know. Okay, now let's look at whatever equations we had for VS2. For VS2 we had two options. One was 1.4 divided by zero point 0.4. This comes out to be, how much does this come out to be? 1.4 divided by,
3.5.
okay, 3.5. Now as long as this quantity, we just need a comparison now, and let's see if that resolves itself or not. So one option is 3.5. This is with action A1. The other is minus, so let me plug in VS1 here and simplify this a little bit. So once I do that, that becomes, that leaves me with a 0.5 plus right 0.5.
Yeah, now after 0.5
So that is telling me
is
this
1.
action gives us the value function to be 1.
Okay.
So
So
now,
given action is
so we got our resolution, right? For S2 the action is A1 and it gives us Vs of S2, V of S2 as 3.5. For S1 again the action is A1 and it gives us Vs1 as 2 plus this value, which is 5.5. And now let's try and look at the MDP itself to make sense if A1 is the probable one or not. A1 is the dashed version. If the choice was just to be done based on S2, then A1 is clearly the winning choice because that has positive reward in both the scenarios. Here there is a negative reward and a big negative reward, so this would be something not chosen as much. So this
it
seems
reminds me
reasonable.
Nash equilibrium method, kind of.
It's I wouldn't use those words in this scenario because we're talking about one agent moving from one state to another. So this is just one learner. There's no opponent with equal intelligence and all of that. So this is not that.
Second agent is the environment that giving probability distribution. It's
Yeah, but the
fine.
environment is not actively trying to destroy your strategy. It's
It's
not
stationary.
intelligent, right? It's stationary. So with this, we have talked about how to use the dynamic programming method and this value iteration method to solve for and get optimal values. Okay, so a very quick recap. We started by talking about what is dynamic programming. Then, based on the idea of dynamic programming, how are we supposed to get the backward induction for these j values. We're supposed to start from the terminal state, go one step back. So look at the states at time n minus 1, then one more step back, and so on until we've finished the whole thing. Then we saw how this can be applied to inventory control problem. First, we started by looking at how these j values are to be written down for different time steps k. Then we actually took a specific case with some constraints on the action, some specific kind of demand, and so on, and tried simplifying for it. And last, this was something not covered in the lectures, no lectures as such, but we also saw what is how to do similar things if what we have is an MDP structure, and what we used was what is called as value iteration method. Uh, Here, what I've written is just the optimal way of doing it. Value iteration is if you take the kth step here and the kth step here and so on. But it comes about to be the same idea in simpler situations, like we saw this example. Actually, even for this example, we had to do a little bit of jugglery, because even though what we got were linear equations, because of the presence of